Good afternoon, ladies and gentlemen. We're back for more. Section 8.2 of our textbook. Okay, and we are on page 577, and I want to go through the examples for this section and hope they touch on everything that you need in order to successfully do the homework. And I do want to preface everything I'm saying before we get started with the fact that it is very important to read the textbook, the sections that we're on, just to kind of give you a feel for what we're talking about in general and gives you an advanced knowledge of where we're coming from and where we're going to. Okay, so that is very helpful. I'm not going to read anything to you, of course, but just to give you that heads up on the importance of understanding what we're doing. And nothing better than reading the textbook, generally speaking. All right, so when we're going to start with this example of number 1, and they want for us to determine the domain and the range of each relation. And remember, in order to remember what the domain is, the domain. All right, come on. Whoop. The domain has to do with the x values. Okay, so the domain will make that association for all the x values. And then the range encompasses all the y values. So in our first example here, these are specific points on the graph, or specific points that go from one to the other without anything in between. So these are basically separate. So the domain, in a case where they give you a relations, ordered pairs as they have here, the domain is going to be all the x values. Okay, so here I've got 2. My next value is 2. Again, I don't really have to list that. I can just list this once because that is all the ordered pairs, that the numbers that it includes. Okay, so what I want to do is just write this as 2, 0, and 3. And this is, and I'll put it in braces or brackets, and that signifies that this set of numbers is the domain. Okay, so I could say D for domain equals this, range R equals, and this will be all the R values. So here I've got 3, 4, -1, and this is supposed to be -1 as well, according to our exercise there. So -1, again, is the same number, so I'll just list it one time. And I'll put my braces around here to give me my domain and range. If this were +1 and this were -1, then I would list all the R values. And that would tell me over here that one of these numbers are duplicated, because I'd have 3 X's and 4 R's. Okay, but for now, this is our domain and range given this set of ordered pairs. Okay, number two here, and it has to do with a graph, and we've got numbers plotted on here to be from -3. Let's see what they have. I'll copy this one. -3, 1, and I'm just going to plot these same points. And it looks like there is 6 of them. I should use a different color. Okay, and what the task at hand here is I'm going to lift this up a little bit. And I'm going to write all the relations of this graph here. So this would be, let's say I'm going to name all these points. So the first one is negative 3, comma 1, negative 2, comma 1, negative 1, comma 1, 0, comma 1, and what did I say? How about 1, comma 1? And then finally 2, comma 1. Okay, 1, 2, 3, 4, 5, 6 ordered pair. And now, what is the domain? What is the domain of this graph, or these points, these relations? So it's going to again it's going to be all the x values. So all the x values on these points is going to be negative 3, negative 2, negative 1, 0, 1, 2. 1, 2, 3, 4, 5, 6. So here's all the x values. So this is the domain. And then the range will be what? I've got 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. They're all 1s. So this is going to be the range. It's all the y values that the relations encompass. And you can see that happening on the graph. All the y values here, every point is with the y value of 1. Okay, in this set of examples where we are identifying functions, we want to determine whether each relation is also a function. And very simply, a relation is a function if the set of relations or ordered pairs have different x values. That is the rule to go by when we're giving this small exercise here. So it says determine whether each relation is also a function. Well, I'm going to look at these relations, and then I'm going to look to see that they have a different x value. So here I got a negative 2, a 2, a negative 3, and a 9. All different numbers. So this is indeed a function. Okay. Take note that functions are allowed to have the same y value, but not the same x value. For example, this has a y value of 5, and this has a y value of 5. However, it does not affect the outcome of these ordered pairs being a function. Okay. Graphically, we can determine if these relations are functions by noting any x values being the same as one way. So here I've got a negative 3, 2. Here I've got a 0, negative 2, and a 0, 3 up here. So these both have the same x values. So notice that they are one on top of each other. And so therefore that in itself refutes this as being a function. Anything else doesn't matter up to this point now. So these sets of points here make this not a function. Okay, and why? Because they have two x values that are the same. So given 2 points. Function is something that just runs, something like this, where it has its own, for every x value, it has one and only one y value. Okay, so here's another x value here, so it has another y value here. It can have the same y value, however, each x value has its own y value. Okay. All right, next problem. I hope that was okay. That's understood. It's the same concept as I said earlier, where it has to be different numbers for the x value. Okay, in our next example here, we have, this is example 7 in 8.2. We have to determine whether the relation y equals 3x minus 5 is also a function. Okay, determine whether this relation is also a function. And you know what the short of it, what we learned in beginning algebra was that our equations that are in the form ax plus by equals c, the equation in standard form anyway, is represents a linear equation. And a linear equation is something that when we graph it forms a straight line, the line in linear. So we worked with many of them in beginning algebra, and in our book going forward we'll be working with them as well. And how you determine that it's linear furthermore is that the exponents of x and y are 1, not squared or third degree, etc., etc., etc. So when we graph these, as I was saying, I could say, if I graph this using the t-chart method, I could say when x is 0, y is going to be 5, negative 5. When x is 1, y is going to be negative 2. When x is negative 1, y is going to be negative 8. So for every value of x I give this equation, I'm going to get a different value for y. So therefore that tells me that this is indeed a function. But I don't have to go through all that. That means I'd have to go through it to infinity. And that would takes too long, of course. I can just look at the problem. The x is to the first degree, the y is to the first degree, so therefore it's a function. Now in this equation, you notice something different. Here I've got that x equals y squared. Okay, so immediately, because the y is squared to the second power, this tells me it's not a function. Okay, but let's get a little deeper meaning of that, what it means instead of just by memorization of that rule. So for example, I could look at this, and if I put a t-chart here, x and y, and I'm going to look at y to give the value for y first, because then I can square it and then I'll spit out what the x is, since x is by itself there. So I could say if y is 3, then x is 9. Okay, I could say when y is 1, x is 1. How about when y is negative 3? If y is negative 3, then x is going to be 9. Okay, why? Because negative 3 squared is positive 9. So now with this 3 samples that I have, what do we notice? I notice that x takes on the same value, and I get a different y value here. So now the problem with that is what was the rule from example 1, the first one we did. X values cannot have the same value. They cannot both be 9. And so this is not a function. Quicker way of determining that, of course, like I said, is this y is raised to the second power. Okay, Different rule applies for when x is raised to the second power. We'll get to that shortly. Not at this time. Okay, as I was saying a little bit ago here, I want to further discuss this idea of when you have a y squared, what the graph looks like, and then we're also going to test our functionality by using the vertical line test. Okay, it was just a very simple test to perform. So notice when I graph these points here, these relations on this graph, what happens? Here, if I graph 9, 3, it's going to be, here's 9, oh, I'm barely on it. Here's 9, and up 3, here's 9, 3. And 1, 1 is going to be here. I'm going to go over 1 and up 1. And then I've got 9, negative 3. And 9, negative 3 is here. So when I connect my dots here, my graph, I guess it's going to look something like this. Okay. And I can see I have a point here and a point here, and these are both on the 9. So that's my first indication that it's not a function. If I can draw a line on the graph and it intersects anywhere on the graph, and it intersects the graph at more than one point, like here it's intersecting the graph here and here and here and here, so what that means is that it fails the vertical line test, and it also indicates it is not a function. It can only be a function if the vertical line passes through the graph at only one point. It cannot go and hit more than 2 points anywhere on the graph. So that one equation we had a moment ago, what was that? It was y equals 3x minus 5. If I graph that equation, I'm going to do it in red. Let's see, if I do the slope-intercept form, I'm going to start at negative 5. And then my slope is 3 over 1, so I'm going to go up 3 and over 1. So now when I grab my line here and plot this, I plotted them already, draw my line, it's going to do something like this, which is that straight line. So looking at it this way, this line is going to take on different values for y for each x that I'm on. So if I have 3 here, so I can just see, here's 3 here. If I move this up to this point, it's going to go over and it's going to touch the line here on the y-axis. If I go over here, I can go anywhere really. I'm going to go up here. My lines aren't straight now, remember that. And I'm going to point this over and it's going to go to this point. So because of the straight line, I'm going to get different values for y for each of the x's. Alright, that's why this is a function, this one is not. This is a function, and this one is not. Okay, next. Okay, for my next set of examples, very easy. It's to use the vertical line test to determine if these lines are functions or if these graphs are functions. Okay, so I've got this blue horizontal line here. If I did the vertical line test to this, as I can see anywhere on this line, on this graph, we can see that it intersects the line at one and only one point. Okay, I could look anywhere. I don't see anywhere that it would possibly hit it twice. Okay, same thing with the green line. These are all separate graphs now. This green line, if I can draw a vertical line anywhere on that line, I can clearly see that it's going to intersect the graph at one point and only one point. And then the blue oval, this was a case where it fails the vertical line test because it is going through the graph at 2 points. Obviously right here and right here. So you can just observe without actually doing the vertical line test to see that it fails it or passes it. That was a quickie. Okay, here's a couple more. The blue line here, this represents a function because this passes the vertical line test. As I draw a straight line, it looks a little suspect here, but I assure you that this line has different y values as we go. So this is passing through at one point. This line here is okay. And of course, obvious out here it is. So this is a function, the blue is. And the green line here is not a function because it just is continuous. I'm just going, if I can't draw a vertical line. I can draw a vertical line, but it's actually cutting right through the whole thing. So it's not intersecting it at one point. It's intersecting it continuously. So this green line would be not a function. This one is not. Green, not. Okay, where the blue is a function. All right, so now we advance to a new objective here where we're going to use function notation. And functions have different names, usually in the form of letters. But we're going to start off with the most popular and using functional notation where, let me start with that y is going to equal f of x. This notation that we call the function of f in x. So f of x, that is read f of x. So y equals f of x. So what that further means is that y, the value of y, depends on x. So y is the dependent variable and x is the independent variable. Okay? So if I have an example here that y equals 4x plus 3, this is what we're accustomed to seeing and using. But now my new language is going to be that f of x, which equals y, equals 4x plus 3. Okay, and that's what it's going to look like. Something like this from here on out. And then I could say something to the effect of, well, what is f of 1 in my notation? F of 1 in 4x plus 3. Now this is telling us to substitute the x with 1. I'm going to substitute the x with 1, and now it's going to be f of 1 becomes y equals 4 times 1 plus 3. And now I can finish this off as y equals 4 plus 3 or y equals 7. Okay, so another way of looking at an ordered pair then would be, well, x is 1, y is 7. And put in my parentheses. Okay, but here's the change that happens after when using functional notation. F of 1 equals 4x plus 3. It now becomes y equals 4 times 1 plus 3. All right, so we'll do a bunch of examples to demonstrate this further. All right, let's use our function notation. Example 14 says g of x, another name instead of f, it's g. G of x equals 3x minus 2. Find g of 1. So I'm going to replace the x with 1 in this equation. And it's going to be 3 times 1 minus 2. So g of x equals 1. And therefore, so you can call this g of x, or you can call it y now. Y equals 1. Another one. G of x equals 3 minus 2. Find g is 0. Again, I'm replacing the x with 0. So then I'm going to have g of x. You can change that to y anytime. G of x equals 3 times 0 minus 2. So you could say y equals negative 2. How about this one? I got a trinomial here. And notice I got an x squared and x. I got 7x squared minus 3x plus 1. It says find f of 1. Okay, so again, that means 1 is going to replace for every x. So it's going to be 7 times 1 squared minus 3 times 1 plus 1. I'm putting all these values of f in parentheses. So when I do the order of operation, I've got 1 squared is 1 times 7. Negative 3 times 1 is negative 3 plus the 1. 7 minus 3 is 4 plus 1 is 5. Same trinomial here. However, it's f of negative 2. So I got a negative number involved here. So I'm going to substitute the negative 2 for each of the x's here. Alright, so, and remember, this could be written, this is written this way to find f of negative 2, but they will say the same thing as we move down the road to say f of negative 2 equals 7x squared minus 3x plus 1. Okay, and that's saying the same thing, to substitute the negative 2 for the x. So it's going to be 7 times negative 2 in parentheses raised to the second power minus 3 times negative 2 in parentheses. It is important to put that negative 2 in parentheses. And then we have plus 1. I mean, you don't have to, but it sure helps me clarify. Now I have less of a chance of making a silly mistake. Because I know negative 2 to the second power is positive 4. 4 times 7 is 28. Negative 3 times negative 2 is positive 6. And then plus 1. 28 and 6 is 34. Plus 1 is 35. Okay. That's that. Alright, let's go through this. I put 2 graphs on one grid. I've got the graph of f, and I also have the graph of g, noted by the colors green and blue. And then we're going to use our color coordination to help us answer these problems that are in this form. Alright, so in example 18, it says, what is f of 4 according to this graph? So remember, 4 is going to be substituted for the x value, and I want to find the corresponding y value. So let's see. On the x value of on the x-axis at 4, which is here, I'm going to follow this up and figure out what is the y value. So I'm just going to go up till I hit it, and then I'm going to go to the left here, and I can see that when x is 4, that y is 2. So f of 4 equals 2. I'm going to do the same thing for b, where f of negative 2. That means when x is negative 2, what is y? So here is negative 2 on the x-axis, and I'm just going to go up. It looks like I'm going up 1, and follow it over to the right. And I can see that when x is negative 2, that y is going to be 1. Okay, now I'll switch over to blue. And that's the G graph. And it's saying G of 5. So G of 5. So when X is 5, what is G? Or what is Y, I should say. G of 5 is Y. So I'm going to go over to 5, follow this up, and I'm going to I'll just call it this spot. Over to my left now is 4. So G of 5 equals 4. Remember, G of 5 then switch over to Y, and then Y equals 4, if that makes a little more sense for you. Okay, and lastly, G is 0. Well, G is 0, that's when X is 0. What is Y going to be? Looks like it just stays there. So when G is, the value of G is 0 is 0. So when X is 0, Y is 0. All right, good. So next, we're going to go the other way, because now they're going to tell us what Y is, and we got to figure out where X is. All right, so find all the values such that f of x equals 1. All right, so f of x equals 1. So let's see, I'm going to say when y is 1, because f of x equals y, it's saying when y is 1, what is x? So here's 1 on the y-axis. So, well, looks like I can go this way, and I've got a x value. Right? It's going to go down here. And then if I go to the left here, I also have an x value, which is here. So now I can say when the value, here's an indicator, all values of such that f of x equals 1, well, now I can say that x equals what? X equals -2 or 2. And notice, it's a function though, right? Because I've got 2 different values for x, in case that thought passes your mind. Looking at the green line here, if I did the vertical line test, it would also pass the vertical line test. So we're covered there. Okay, so let's try find all the values such that g of x equals 0. So when y is 0, what is x at that point here? Well, looks like it's just going to be 0 again, right? I'm going to have one value. So when y equals 0, x equals 0. That was a little easier one. Okay. All right. All right, that's that for that example. And let's see what else we got to do here. Graphing linear functions. Okay, we've done that before, and I'll let us stop here for this section.